Hello everybody, welcome to chapter 21, which is about electromagnetic induction. In this chapter, we will learn about the phenomenon of induction, magnetic flux, Faraday's and Lenz's law, eddy currents, self-inductance transformers. In the end, we will talk about magnetic field energy as well as RL and LC circuits. The picture you see here on the right-hand side are large generators in a power plant. As you can imagine, a human is about the size of twice the railings that you see. These are very, very large electric motors that are spun by the power of either water, steam, etc., in this case probably water, and that are used to produce energy. If it wasn't for the concept of induction, we would not be able to have electricity as easily as we have today. Induced currents play a very important role in everyday life. We have, as I just said, power generation in power plants or the dynamo in your bicycle. Magnetic recording and data storage really relies on inductive principles. Basically, every time that you read and write data from a hard drive, an inductive type process flips bits. The other one is, for example, the dark stripe on the back of your credit card has magnetic grains embedded in them. You can store bits, and due to induction, you're able to read data of the credit card and then perform a transaction. And the other one is wireless energy transmission. If you look at your toothbrush at home, if you have an electric one, you will see that there is no physical metallic contact on the toothbrush. It's plastic against plastic, and it's actually through induction that you can actually charge the device. Another interesting application of induction is so-called inductive cooking, where you basically have a metallic, a plate where you put a metallic pot on. In this pot, currents are induced, and as such, only the pot heats up, and you basically cannot burn your fingers by putting your hand onto the cooktop. So what we want to do is we want to understand how these phenomena work, and in particular, when currents are induced in a conductor by a magnetic field. For this, we're going to do the following simple examples. So what we're going to do is we're going to study first the following cases. First, we have a coil connected to a galvanometer. Note that the system has no EMF source connected to it, meaning that we expect to see no current in the meter. If we now take a magnet and place it close by and don't move, what do we observe? Again, we observe that nothing happens, meaning that there is no EMF induced in the system. However, if we do the following experiments, we actually find that something is induced. For example, on the left-hand side, you see that whenever we move the magnet towards and away from the coil, we actually see a reaction in the galvanometer. Whenever we put a second coil, in other words, a source of magnetic field close to this coil, and we move it towards and away, we'll see a reaction. And also when we use a DC current from a battery, when we switch things on and off, as shown in the right-hand side, you see a reaction. So what we notice is that by changing the properties of the system, in the sense that we change the magnetic field and or the area, and this is known as the magnetic flux, which I will introduce in the next slide, we actually have an induced current. And this induced EMF is called the induced EMF. Now, what is the magnetic flux? It's analogous to the electric flux. You see the picture here on the right-hand side. You have some surface. You take a little patch of area delta A, and you compute the magnetic field component B perpendicular that is perpendicular to this surface. B perpendicular is then given by the magnitude of the magnetic field times the cosine of the angle, and the magnetic flux through this area element is then going to be delta phi equals the perpendicular component times delta A, which is the same thing as B delta A times cosine of the angle. And the total flux then is nothing else than the sum over all these little flux contributions through the little areas. In other words, we just perform the sum over these, which corresponds to what we call a surface integral. Now let's look at the spatial case of a planar surface with a constant magnetic field. In this case, the magnetic flux is just given by the perpendicular component times the area A of this rectangular surface, in other words, BA times cosine of the angle. The SI unit for magnetic flux is called the Weber, shortcut WB, and 1 Weber is 1 Tesla times meter squared, and if you use the definition of Tesla, you see that it's 1 Newton meter per amp. At the bottom, you see 3 pictures that nicely illustrate what's happening whenever the angle phi is 0. In other words, whenever the magnetic field is perpendicular to the surface, the flux is going to be maximal, meaning that B times A. However, whenever the surface is at an angle phi to the magnetic field, the flux is just going to be BA times the cosine of the angle. And whenever the angle is 90 degrees, in other words, in this particular case, the surface is parallel to the direction of the magnetic field, you basically will have no flux through the surface. And this leads now to a very important law known as Faraday's law. Faraday was an English scientist in 1791 to 1867, discovered the relationship between an induced EMF and a changing magnetic field. Flux, to be precise. I want to emphasize that whenever you change the flux in the system, you induce something. And Faraday's law says the following. The magnitude of the induced EMF in a circuit equals the absolute value of the time rate of change of the magnetic flux through that circuit. In other words, the EMF is going to be delta flux divided by delta T. Note that we take the absolute value, and the reason for that is that it is not clear a priori in what direction this EMF will go. So in this definition, the EMF is positive, and if you have a coil with n turns, what you have to do is replace E by the number of turns, n times E. Let me show you an example. For example, we have a voltage induced in a loop of an area of 120 centimeters squared with a field that is increasing at a rate of 0.02 Tesla per second. What this means is that the EMF is going to be the change in flux divided by the change in time. However, the change in flux is going to be the change in field times the area per time. We know that the change in field per time is going to be 0.02 Tesla per second. We multiply this by the area and we obtain 2.4 times 10 to the minus 4 volts. Again, I would like to emphasize that the sign of the voltage is not determined. Now let me show you another example. A coil has 100 turns and a size of 10 by 10 centimeters. By size I mean cross section. The coil is rotated from an angle of 45 degrees to an angle of 90 degrees to the field in 5 seconds. If the field is 1 Tesla, what is the average EMF induced? Again, the induced EMF is going to be d phi over dt. However, we don't know what the change in the flux is. So at the beginning of the process, phi b1 is going to be times a times the cosine of the first angle. And phi b2 is going to be b times a times the cosine of the second angle, which means that the change in flux is going to be the area times the B field times the number of turns multiplied by the cosine of the changes in angles. And when you plug everything in, you obtain 1 Tesla times 10 to the minus 2 meters squared times the 100 terms times 1 over square root of 2, which is the cosine of 45 degrees minus the cosine of 90 degrees, which is 0. And what you obtain now is that this is 1 over square root of 2 Webers. So the EMF then is just going to be this change in flux divided by delta T. Delta T is 5 seconds, so you obtain 1 over 5 square root of 2 volts. Let me show you another example, which is basically a schematic for what is known as a railgun. A railgun is a device that allows you to accelerate a projectile that is magnetic in a magnetic field. So the goal is to accelerate this crossbar that you see here connecting this U-shaped wire to 300 meters per second using a 9-volt battery and 2 rails that are 2 centimeters apart. So the length between the rails is 2 centimeters. And the question is, how large must the magnetic field be such that the bar moves? Note that the magnetic field points into the slide or into the wall because we want this, this bar to move to the right. The solution can be computed in a simple fashion. The EMF is going to be d phi over dt, which in this case is going to be B times delta A over dt. Why? The reason is that the magnetic field B is constant. However, whenever this bar is moving, what you're changing is actually the area that is enclosed by this circuit. In this delta A is just going to be the length of the crossbar times the amount of path that it has traversed, so this delta S. And delta S is related to the velocity times delta t due to the simple relation that velocity equals distance divided by time. When we plug everything in, we obtain that E is going to be B times L ds, which is the same thing as B times L V dt divided by dt, and the result we obtain is magnetic field times the length of the bar times the velocity v. This allows us to solve for B, and we obtain 1.5 Tesla. So any strong neodymium magnet of about 500 grams should be able to do the trick. I would like to emphasize this is an academic example. It isn't as simple as it is portrayed here, and please do not do this at home. I don't want to have any accidents. Now, what I would like to do is also revisit the generators that we talked about in the previous chapter. Remember, the principle of a generator is that we have a coil of some area A that rotates in an external magnetic field B. And this then produces an EMF. On the left-hand side, you see a schematic of a generator. You basically have two contacts A and B that you would, for example, connect to a light bulb. You have this rectangular wire hoop that has a cross-section A and that rotates in a magnetic field that lies in the plane and horizontally pointing to the right. When you start with the loop being vertical, in other words, fully perpendicular to the magnetic field, the flux is maximal, and you see this on the right-hand side. The top line shows you the head-on view of this loop, and you see that at the very beginning it is facing vertically and the magnetic field is facing horizontally to the right, meaning the flux is biggest. And then the hoop starts rotating, and now you have to basically see what happens at the point where now the flux is zero, meaning that the hoop is perfectly horizontal in the field. The flux is of course zero because it goes like the cosine of the angle. But if we now trace this change in the flux, which corresponds to the change in flux by time, which means the EMF, you see that it's going to be maximal where the curve for the flux has the biggest change in slope, and this is around where phi equals 0, in other words, the derivative of the cosine function. And you see very nicely that the induced EMF is going to be minus d phi over dt, which gives you a sine function. This is summarized in this slide here. The generator starts perpendicular, and at any given point in time, the flux is going to be B times A times the cosine of the angle. Because the EMF is going to be the change of flux by the change of time, it follows that the EMF is going to be omega BA sine omega t. And as you can see, the resulting current is an alternating current, which is why we call this generator an alternator or AC generator. Now with this, I'd like to move on to Lenz's law, which is actually very, very important. Lenz's law basically tells us now in which direction the induced EMF or current has to point. And what it states is that the direction of any magnetically induced current or EMF is such as to oppose the direction of the phenomenon causing it. A simple example, let's have a ring in an increasing magnetic field. You can see this depicted on the right-hand side. The magnetic field is increasing from B to B plus some delta B. And what Lenz's law says is that whatever will be induced has to be produced by a field that opposes this change. So Lenz's law states that this induced field must oppose the direction of the original field. So if the change is going vertically up, it means that the induced field has to point down. And now when you use the right-hand rule, and you do this by sticking your 4 fingers through the hoop, pointing in the direction of the B field, you will see that your thumb actually points now in the clockwise direction, which tells you in which direction the current is going to go. Now there are of course different scenarios that you can study, for example, here in the left-hand side picture, if the north pole faces the loop and the magnet is moving down, what you're actually doing is you're increasing the magnetic field, and because the area of the loop is constant, still the flux is increasing. This means that the induced field has to oppose this change in flux, and if you now use the right-hand rule, you obtain a current that goes counterclockwise. If you now do the opposite in the sense that you push the south pole into the loop, so from top to bottom, this is shown on the very right, then in this particular case, what you're having is a flux that is actually increasing, but it's increasing in the other direction. Remember that magnetic field lines go always from north into south poles. So you have an increase in flux, but this flux is pointing upwards, which means that B induced has to point downwards, which therefore means, if you use now the right-hand rule, that the current goes clockwise. We can revisit the problem, for example, here on the right-hand side, and I will only discuss this case. If now you have the north pole that is facing down and you're pulling the magnet upwards, what you're actually doing is you are reducing the flux. This is shown here in the lower panel, where you see that phi by 1, B1 becomes phi B2, and so it changes, it shrinks by amount delta phi, and this means that now the induced magnetic field wants to point in the same direction as what is causing it. In other words, and this might seem a little confusing now, what it's doing, it's pointing opposite to the change in the flux, but it's now, because it's going the same direction, it's decreasing, it's going to point in the direction of the original B field, and what you obtain here using the right-hand rule is that the current again goes clockwise. I will show you multiple examples in the next couple of slides. First, I would like to revisit the railgun. So what happens when we move the rod by hand at a given velocity v? In which direction does the current go? Well, remember, the magnetic field points into the plane and is constant. However, when we are actually pulling this rod motion towards the right, what we're doing is we're increasing the area of the loop. This means that we're actually increasing the magnetic flux. This means that the induced field has to actually point in the opposite direction of the field that is causing this. In other words, instead of pointing into the slide, it has to point towards you. And if you now use the right-hand rule for the induced field, you will see that the current actually flows counterclockwise. Let me show you another example. We have the following scenario here. We have a field pointing into the slide. We have a rectangular wire hoop, and in this particular case, the magnetic field is decreased. So if the magnetic field is decreased, what this means is that the flux decreases. This means that the induced field has to point in the same direction as what is causing it. And if you now use the right-hand rule and, for example, point now your 4 fingers through the hoop into the center, you will see that your thumb points in the clockwise direction, meaning that the current that is induced actually flows clockwise. Let me do another example. In this particular case here, we have a wire with a current I, a straight wire, and this current is increasing. And we have a metallic hoop, and the question is, in which direction does the current in the hoop go? So if we have a current going to the left, unlike right as is written on here, in the straight wire, we can use the right-hand rule, and we will see that if our thumb points in the direction of the current, our 4 fingers will actually point into the slide at the area where this hoop is, meaning that up there the magnetic field, here depicted in red, actually points into the slide. Because the current is increasing, it means that the induced current has to oppose what is causing it, and so in blue I show you the induced magnetic field that actually points in the opposite direction of the B field that causes it. Now you have the induced field pointing towards you and out of the page, meaning that if you now use the right-hand rule, your thumb is going to point in the counterclockwise direction, meaning that the induced current will actually go counterclockwise. The final example I want to show right now is the following. We have the following scenario. We have a metallic hoop that is flying in vacuum where no magnetic field is into an area between A and C that actually has a magnetic field. And what we want to know is in which direction does the induced current go when the hoop flies through the system. So at point A, this hoop is slowly penetrating the area with magnetic field. And if you think about this, what this means is that while it's flying through there, the magnetic field that is surrounded by the metallic hoop increases, meaning that the flux is increasing. Because the flux is increasing, it means that the induced field has to oppose what is causing it, so it points into the plane. And if you now use the right-hand rule, what you obtain is that the current goes clockwise. In zone B, the hoop is completely in the magnetic field, and while the hoop might be moving, the flux is constant. Because the flux is constant, it means that the induced B field is zero, meaning that we have no current. Now, in part C, let's see, is the part where we're actually exiting now the area with a magnetic field. In this case, the flux is decreasing, which means that now the induced field has to be in the same direction as what causes it, which means that B induced is parallel to B, in other words, out of the plane. And if you use the right-hand rule, you now obtain that the current flows counterclockwise. And then finally, when the hoop is in part D, you have no magnetic field anymore, and at that particular point, because you have no magnetic field, you have no flux, and because you have no flux, it means that you have no induced current. The final example that I would like to show is the following. What we want to do is we want to calculate the induced current in this rectangle that is moving at a velocity v in a magnetic field of 1.25 Tesla, and it has a resistance of 12.5 ohms. The current is given by the EMF divided by the resistor R, so we have to calculate the EMF. And remember, we calculated that earlier for the case of the railgun, and we showed that E was V times B times L, where V is the velocity. So in a time delta t, it moves by a certain amount, and you can calculate the change in flux. You can say that delta phi is B times delta A, which is BLV times delta t, like we did before for the railgun. And so you obtain that the EMF is BLV, which is 2.81 volts. You divide this by the resistor and you obtain a current of 0.225 amps. And this leads us now back to another concept known as the motional electromotive force. When a conductor moves in a magnetic field, we can gain further insights into the induced EMF by considering the forces and charges in the conductor. Let's look at the scenario shown here on the right-hand side. You have a metallic rod that is moving to the right in a magnetic field that points into the plane. Any charge Q inside the system will therefore experience a force that is equals Q times V times B. If now B points into the plane and V is to the right, the force will point upward, which means that inside the bar a charge imbalance occurs because positive charges move to the top, therefore producing an electric field between the points A and B, in other words, the long extremes of the bar. And this electric field that forms produces now a downward force on the charges. This will continue to happen until we have a balance of the forces, in other words, until the magnetic force equals the electrostatic force, which is the charge times this electric field. In other words, a potential will build up, and the potential between points A and B will be given by the length of the bar times the electric field, where the electric field is just given by the velocity times the B field. In other words, you obtain a potential that is going to be the velocity times the B field times the length of the wire. Now, let's Look at again the case we studied before. Suppose the rod slides along this U-shaped conductor. The circuit is complete, no magnetic force acts on the charges in the conductor, but there is an electric field caused by the accumulation of charges at A and B. Remember that if you want any charges to move, you need to have an electric field. This is the exact same thing if you, for example, want water pressure in your pipes at home. You need a water tower that produces a potential difference, therefore producing pressure. Now, under the action of this electric field, a current is established counterclockwise, and the moving rod has become now a source of EMF with charges moving from the higher to lower potentials. In some ways, you can see this rod as a type of battery. The EMF is called a motional EMF, and when the velocity, magnetic field, and rod are mutually perpendicular, this motional EMF will be given by E equals velocity times B field B times the length of the bar. Note that this is analogous to a battery, however, the EMF source is different. Before I move to inductance, I would like to say a few brief words about eddy currents. So far, the currents induced by a magnetic field have been confined to well-defined paths, for example, thin wires. However, you have electric equipment that will have large metallic pieces moving in a field. And the currents induced there behave like eddies in a river, in other words, eddy currents. An eddy in a river is basically a little swirl produced by something that's constricting the path of the water. For example, if we now study a large circular metallic plate and only one zone in this plate is actually exposed to a magnetic field, as shown here by this light blue circle, you will obtain downward currents at the direction OB that induce a force opposed to the direction of rotation due to Lenz's law, and these return currents will lie outside the field zone, so actually no force occurs. So what you have is, as you see on the right hand side, these eddies or swirls of currents going around. Now these eddies will cause a braking action where electrical energy is converted into heat, therefore producing a braking force that is due to the resistance of the material. Now you might think that this is just a useless effect. However, it is one of those effects that can be used for many technological applications. The first one that most of you have probably sat on is the ergometer. A stationary bicycle, at least from the modern kind, has nothing else than a big metallic disc inside that you can see as a fly disc. However, you can put magnets closer and further away from this disc, therefore increasing the amount of power that you need to rotate the disc, therefore making you work out harder. A similar system is used also in the braking system of electric vehicles, for example the Toyota Prius, where actually you have such discs that will be used then to charge the batteries of the system and at the same time play the role of brakes when the system slows down. Finally, another system that actually uses this type of technology, however in a very different way, is the TSA security gate. In that particular case, what you have is you have a transmitter and a receiver. The transmitter sends a magnetic field out. If you now have some metallic object in your suitcase, this will produce eddy currents that produce an additional magnetic field. The receiver is tuned to only measure the transmitted magnetic field, meaning that it can detect the additional field due to the eddies, and therefore it will give a loud beeping signal, and you'll have to go to secondary screening, strip all the way down, bend over, and be very, very unhappy with the TSA officers. I would like to now move on to the concept of mutual inductance. The question I want to ask you is, how can, for example, a 12-volt car battery provide thousands of volts needed to produce sparks in the engine chamber? And the answer for this is known as mutual inductance. The concept is very simple. You have a changing current in one coil that induces an EMF in some adjacent coil. You see the scenario depicted here on the right hand side. You have current coil 1 that carries current I1 and has N1 turns. It will produce a magnetic field B that is shared by coil number 2 that has N2 turns, and therefore you have a flux Phi/2 produced by the magnetic field of coil 1 going through coil number 2. So the current in I1 in coil 1 will produce this flux which passes through coil 2, and therefore we can calculate now the EMF in coil 2, which is going to be E2, which is a number of turns of coil 2 multiplied times the change d phi B2 divided by dt. However, the flux in coil 2 must be proportional to the current I1, meaning that the number of turns N2 times phi B2 has to be some proportionality constant, let's call it M21, times the current I1. We can now divide both sides of the equation by delta t, and you obtain that N2 d phi B2 dt equals M21 di1 dt. The left-hand side of this equation is nothing else than the definition of the EMF induced in coil number 2, so it follows that the EMF induced in coil number 2 is going to be proportional to the change of the current in coil number 1, and this is all multiplied by some proportionality constant, which in this case we call M21. You can do the exact same argument the other way around. When you do the math, what you find is that the EMF induced in coil 1 is going to be another proportionality constant times the change of the current in coil 2 per time. Now, due to symmetry considerations, it must follow that this constant M12 has to be the same thing as the constant M21, and we call this the mutual inductance M. What is the definition? The mutual inductance of two coils is given by M equals N2 phi B2 divided by I1, which is the same thing as N1 phi B1 divided by I2. And from this it follows that the EMF in coil 2 is going to be the mutual inductance multiplied by the change in current on coil 1 and vice versa. The SI unit for mutual induction is called Henri or Henry for the Americans, and 1 H or Henry equals 1 Weber per amp, which is 1 volt second per amp or 1 ohm times second. Notice this interesting relationship that these Henrys are somehow related to the unit of a resistance, these ohms multiplied by time, and we'll get back to this in the next chapter. If the coils are in vacuum, M depends only on their geometry, and if the magnetic material is present, M will depend on the properties of this magnetic material. Now, let me show you how to compute these mutual inductance now for a system of two coils that are wound around each other. We have the following scenario. We have a 0.1 meter long solenoid of diameter 0.02 meters that has 1,000 turns. We have a second coil that is tightly wound around it with only 100 turns, and the question is, what is the mutual inductance? The definition of this mutual inductance M is going to be the number of windings on coil 2 times the flux divided by the current on 1. And the flux on 2 is going to be the area, which for both is going to be the same, times the magnetic field. Now, because the coils are tightly wound around each other, it follows that both have to have the exact same magnetic field. If we go back to the previous chapter, for a long coil, the magnetic field B1 is going to be the constant mu naught N1 current on 1 divided by its length. So it follows that the flux on 2 is going to be the area A, which both share, times B2, which is the same thing as the area A times B1, which is going to be A times mu naught N1 I1 divided by L. So now we know the flux on 2. We can plug this now in the definition of mutual inductance here on top, and what follows is that M equals N2 phi 2 divided by I1, which is the same thing as N2 over I1 times A mu naught N1 I1 divided by L. You see now that the I1s cancel out, and you obtain for the mutual inductance mu naught N1 and 2A divided by the length. Notice that this expression only depends on the geometry of the problem, in other words, N1 and 2, the area and the length, and not on any other property of the system like a current or a B field, meaning that this is really a proportionality constant. If we now plug in the numbers for the diameter and the length, for this particular case, if I did the math right, we obtain 40 times pi squared microhenry. Now, In the previous slide, we talked about the concept of mutual inductance, where a changing current in one coil induces an EMF in a second coil. However, if you think about it, if you just look at one inductor, also known as this coil as is depicted here on the right hand side, if we have a current that continuously changes in the system, this would actually induce or produce a magnetic field, and this magnetic field would at the same time now induce an EMF in the coil itself. This effect is known as the self-inductance. For example, let's look at a coil with N turns carrying a varying current I. What you have is a magnetic flux that passes through the coil, and you can define the self-inductance capital L of the circuit as N times the flux divided by the current I. If the flux and the current change with time, you can use this and write it as N d phi dt equals L di dt. If you now compare to previous expressions, the left-hand side is exactly the expression for the induced EMF, and it follows right away, using Faraday's law, that the magnitude of the EMF due to self-inductance is going to be N d phi dt. So we can define this self-inductance L as follows. It is given by the magnitude of the self-induced EMF E per unit rate of change of the current, such that E equals L times the I dt. From this definition, it's clear that the units are the same for the mutual inductance, which is this Henry, and you see that L again is expected to be a constant. Now, part of the circuit is designed to have a particular inductance is called an inductor or choke. The reason we call it a choke is because, as you can see, the higher the rate of change is of this current with time, the stronger the induced EMF, and as we will see in the next couple of slides, the induced EMF always opposed what is causing it, meaning that if you have a high frequency signal, you will actually filter it out. And these inductors are actually indispensable in electric circuitry, and the circuit symbol is a twiddly line connected to the usual wires that we use. Now, what is the direction of the self-inductance? The direction of the self-inductance can be determined from Lenz's law. And again, as I just said, the EMF wants to oppose the rate of change in the current. So for example, in the first case, where we have a constant current, there is no self-induced EMF, therefore the voltage is 0. In the case of an increasing current, the IDT is positive, meaning that the EMF opposes the current, and so the voltage between A and B will be positive. And when you have a decreasing current, in this case the IDT is negative, and therefore the EMF points in the same direction as the currents, so the voltage will be negative. So one way to see this is that, especially in the case where things are increasing, when you try to increase, the self-inductance is going to try to hinder you in doing this and try to, quote-unquote, slow you down. Now let me give you some final considerations. The inductance of a circuit again depends on its size, shape, and number of windings, and for a coil with N turns close together, the inductance is proportional to N squared. I will do this calculation in the next slide. The inductance depends on the magnetic properties of the material enclosed by the circuit. So for example, if you have some iron core and you wind a wire around it, depending on the material, in this case iron, you will get a different self-inductance. If the flux is concentrated in a region filled with a magnetic material, then what you have to do in any calculation is replace mu naught by mu, which is Km times mu naught, and Km is known as the permeability. For example, for a soft iron core, Km can be 5,000, and this is why iron and ferrite cores are used in technological applications, meaning that the effect is actually magnified, in this particular case, 5,000-fold. Now let me compute the self-inductance of a solenoid with cross-section A and length L. The self-inductance is defined as N, the number of windings, times the flux divided by the current. Remember that the flux is going to be B times A, the B field times the cross-section A, and the B field for a long solenoid is mu naught Ni divided by the length. we can plug the expression for B in the expression for phi, we can plug the expression for phi in the expression for L, and we obtain that L is n phi over I, which is n mu naught n IA divided by I times L. Again, you see the factors of I cancel out, and you obtain that the self-inductance is going to be given by mu naught n squared A divided by L. Again, this does not depend in any ways on current or magnetic field. It only depends on the geometry of the system, and if this were now wound around some iron core, mu naught would be replaced by Km mu naught, where Km is the magnetic permeability. What I would like to talk about next is transformers, and I'm not talking about the ones from TV, but the ones that have very important technological relevance. What is the advantage of an AC over DC current? The advantage is very simple. It is easier to step voltage levels up and down. In other words, it makes your life easy when you change the voltage, say from 120 to 12 volts. Examples are long distance power transmission. You want to increase first the voltage to 500 kilovolts. Then you want to transfer this across the wires, and when you have a very high voltage, you actually reduce the dissipated power. Then you want to step it back down to what you get in the household. In America, this would be 120 volts. In Europe, 240. This is particularly a problem when you travel because you might be careful when you plug appliances from one country into the other. And then finally, cars, for example, use 12-volt batteries but require high voltages for sparks. And the way we do this is with transformers. I would like to emphasize that in the following discussion, voltage just represents the maximum of a sinusoidal varying voltage. Okay? In reality, and as we will see in the next chapter, these voltages that you get fed by an AC source actually oscillate harmonically with time, meaning that at any point in time the value can be somewhere between two maxima. Now, AC voltages are usually described by the root mean squared or RMS values. This means that the peak voltage in a household will be 120 times square root of 2 volts, which means that the peak value of what actually comes out of the wall is 170 volts. Now, how is the transformer constructed? It consists of two coils that we call windings that are electrically insulated from each other but are wound around the same iron core. You see a schematic here on the right hand side. In this particular case, you have primary winding with N1 windings, one wound around the iron core, and you have the secondary winding with N2 windings that we call, as I said, the secondary. And typically the primary is connected to your source and the secondary is connected to, say, a resistor or whatever device you want to change the voltage to. The circuit symbol is two twiggly lines separated by two solid lines. Remember the circuit symbol for an inductor, so you just separate it by this iron core. Now, how does it work? It's a very simple device. An AC current in the primary sets up an alternating flux in the core, and according to Faraday's law, this induces an EMF in the secondary. We can now do the same calculation we did before. However, we make the following assumptions. First of all, the flux is confined to the core. The flux is the same in the primary and secondary, and we are going to neglect resistance of windings. The induced EMFs in coils 1 and 2 are going to be E1 equals N1 d phi dt and E2 equals N2 d phi dt. Now the flux d phi dt has to be the same in both, actually the change in the flux, meaning that E2 divided by E1 has to be the same thing as N2 divided by N1. And because we assume that the resistances are zero, we therefore obtain for the terminal voltages that the voltage on the secondary divided by the voltage on the primary has to be the ratio N2 divided by N1. In other words, the number of windings on the secondary divided by the number of windings on the primary. By choosing this appropriate Turner's radius, N2 divided by N1, we may now obtain any desired secondary voltage from a given primary voltage. If V2 is bigger than V1, we actually have a so-called step-up transformer, and if V2 is less than V1, we have a so-called step-down transformer. Now, a quick word about real transformers. In real transformers, there is some power dissipated due to the resistance of the windings, and also power is dissipated due to eddy currents. If you have a big iron block where you wound your wires around, you're going to get big eddy currents, and the way that technologically this is prevented is by using so-called laminated cores or the use of ferrites, which have very poor long-distance power transmission properties. So in this case, for the eddy currents on the right-hand side of the laminated core, we will have very small ones, which is not the case on the left-hand side. Now let me show you a calculation using a transformer. The goal is to convert 110 volts to 12 volts, and the question is, what is the winding ratio of the transformer? We use the equation for transformers that E1 divided by E2 is going to be N1 divided by N2. So we just look at the ratio N1 over N2, and this is going to be 110 divided by 12 volts, which gives you 9.17. For example, if on the secondary we have N2 equals 1000, this means that N1 will need to have 9170 windings such that you can convert 110 to 12 volts. Now at the end of the chapter, I want to discuss magnetic field energy. What we want to do is we want to calculate the energy input U needed to establish a final current I in an inductor with inductance or self-inductance L if the initial current is 0. The way we do this is we actually let the current at some instant be I and its rate of change be the I dt. What we then can do is we can look at a terminal voltage at that particular instant, and that's going to be V equals L di dt, given the equations we just learned for self-inductance. And now we can look at the average power supplied by this current during a small interval delta t. And this power is just going to be the terminal voltage times the current I, which is going to be L di dt times the current I. Now the energy delta U that is supplied for the power to increase by that little bit during this time interval is going to be approximately delta U time, which is equals to P times delta T, which if we plug everything in is going to be Li di. So again, we start off with the EMF, which is L di dt. We calculate the power, which is going to be the voltage times the current. We plug everything in. The energy needed to increase the current by a little amount delta is going to be delta U, which is power times delta T, which is Li di. Now if you want to know what the total energy is that is needed to increase the current from 0 to a value capital I, what we need to do is we need to sum over all these contributions. And to actually do this, we have to perform an integral, the integral of I di, which gives us as a result that the energy stored in an inductor is 1/2 Li squared. We can think of this energy U as analogous to a kinetic energy associated with the current, and this energy is 0 when there is no current. In the same way that there is no kinetic energy when, for example, a particle is not moving, in other words, when the velocity is 0. The energy of an inductor is stored in the magnetic field within the coils in a similar way that the energy in a capacitor is stored in the electric field between the plates. Now, in analogy to the case of the capacitor, what I would like to do now is compute the magnetic field energy density inside some confined space. For this, we're going to look at a very simple case. We're going to look at toroidal solenoids, simple geometry. The field is constrained to this core. And what we want to do is we want to use the equations we learned before. First of all, we need to know what L is, the self-inductance. By definition, is N times flux divided by I, but the flux phi is B times A, and for the toroidal inductor, we have B equals mu naught N times the current divided by 2 pi R. When we plug everything in, we obtain that self-inductance is going to be mu naught N squared A divided by 2 pi R. We can now plug this into the equation for the energy U, which is 1/2 Li squared, and we obtain the expression that you see here at the bottom of the slide. Now to calculate the magnetic field density, we need to divide the energy U by the volume of the torus, and the volume of the torus is 2 pi R times A. Where does this come from? you can think as a torus as a rectangular box that is bent together to be shaped like a ring. The volume of a box is going to be the cross-section A times the length of the box, and in this case, the box has length 2 pi r, which is the circumference of the circle. Again, we take the energy, divide by the volume, and plug everything in. What we obtain is the expression on the right-hand side. The energy density little u is 1/2 mu naught n squared I squared divided by 2 pi r squared. And now we remember, as we saw in the previous slide, that the B field is mu naught n times the current divided by 2 pi r. What we obtain now for the magnetic field density is it is 1/2 mu naught times the magnetic field B squared. Note that, and we can do this in this class because it is too complex, that this expression is valid for any geometry, and in particular for the energy density due to an electric field. Remember that it was 1/2 epsilon naught E squared. In other words, there is some given symmetry between these two systems. This will become far more apparent when we talk about electromagnetic fields in the following chapters. Let me do now a final example problem. What is the energy stored in an inductor with a self-inductance L of 10 to the minus 6 Henry and a current of 10 amps? We use the expression U is 1/2 Li squared, so we have 1/2 times 10 to the minus 6 Henry times 100 amps squared, and what we obtain is 50 microjoules. This is a small amount of energy. However, as you can imagine, the larger your inductor and the more current you push through the system, the larger your energy will be. In the last part of this chapter, I would like to discuss the RL and LC circuits. Let's look at the circuit depicted here on the right-hand side. We have an EMF source with EMF E. We have a switch. Then we have in series a resistor R and an inductor L. And what we want to do is we want to study the potential differences across the inductor, which are VAB equals IR, and we use here little letters for time-dependent quantities, and the potential difference VBC between B and C across the inductor, which is going to be L dI dt. Now, suppose the switch is closed. The current will not instantly reach a given value because this would mean an infinite induced EMF in the inductor. So actually, what we are having is that if the current would go immediately to its max value, the IDT would be infinite, meaning that the potential in the inductor would be infinite, and we know this is not the case. So the rate of growth of the current depends on the induction L. Now let's just say the IDT is the rate of change of the current I. As I just said before, the potential difference across the inductor is going to be L dI dt. And across the resistor, the potential difference is going to be I times R. We can now apply Kirchhoff's rules, and we started, for example, by counting between the switch and the EMF, and we were going to have E minus IR minus L dI dt equals 0. This comes from E minus VAB minus VBC has to be 0. If we now divide everything by L, we obtain the following equation. The rate of change for the current is given by dI dt equals E over L and minus R over L times I. So let's study this equation in a little bit more detail. At the instant the switch is closed, in other words t equals 0, we still have no current. And in that particular case, the I is going to be 0 in the previous equation, and the IDT is going to be E over L. You see, therefore, that the slope of the current increase, is the IDT, is going to be given by E divided by L. In other words, the bigger L, the smaller the slope, the smaller L, the bigger the slope. And this is because Lenz's law, the inductor is going to try to work against what is causing the induced current, meaning that it's going to try to slow down the flow of charges. So the greater the inductance, the slower the current increases. Now when the current reaches a steady state value I, the rate of change is going to be 0, so the IDT is going to be 0. And this means that E over L minus R over L times capital I here being the steady state value, is going to be 0, and from this it follows that the current is now given by plain vanilla Ohm's law, I equals E over R. So when you look at the picture at the bottom right, you see that the current grows, and the rate of growth depends directly on 1 over L. And once you wait a very long time, the current will go into a steady state value I, which is this horizontally dotted line. We can actually solve the equation that describes this process. It's known as a differential equation, and in that particular case, we obtain for the current as a function of time that it is going to be E divided by R times 1 minus e to the minus R over L times t. So you can find now a characteristic timescale tau, and at tau equals L over R, which is a time constant, the current will have risen to a value of 1 minus 1 over E. Let's now do the opposite process. Suppose now that the switch S1 has been closed for a long time until we reach the steady state. In other words, the current has now a constant value, the rate of change is 0, meaning that the inductor has no effect on the system. Now you close switch S2 at, let's say, time t equals 0 to bypass the battery. In this particular case now, the battery is disconnected, and now we can see what happens in the system. Again, we can apply Kirchhoff's rule to the bottom loop. And what you have is that the IDT is going to be minus R over L times I. Where does this come from? You start counting, for example, at the switch S2, and you're going to have minus IR minus L, the IDT has to be 0, from which the IDT equals minus R over L times I. If you solve this differential equation, you obtain that the current I varies as the steady state value I0 times exponential of minus R over L times t. Again, we have the same time constant describing the process, and so the time required for the current to decrease to 1 over E is going to be L over R. I would like to also mention briefly that one can show that the energy that is stored in the inductor decreases at a rate equal to the dissipation rate I squared times R. Now, in the previous chapter, we discussed the RC circuit. We saw there a similar behavior with this exponential decays and increases. Now we studied the RL circuit, where we also saw exponential behavior. And this is because a resistor R always causes dissipation. What we'd like to do at the end of this chapter is study now the LC circuit. And this is a circuit comprised of an inductor L and a capacitor C that is depicted here on the right-hand side. In an LC circuit, the stored energy actually oscillates between the capacitor and the inductor, and what we actually obtain is an electrical oscillation. You can show that the total energy of the circuit is constant, and this is reminiscent of kinetic/potential energy conservation in a pendulum. When you have a pendulum, whenever the pendulum reaches the extreme values, you have a maximum in the potential energy. The kinetic energy is 0 because the pendulum stops moving for a split second. However, when it is going through the point where the spring, for example, or the pendulum is in the relaxed position, the velocity will be maximum, meaning the kinetic energy is maximal, the potential energy will be 0, and when you look at the sum of kinetic and potential energy throughout the process, what you will find is that these are always constant. The oscillation occurs with an angular frequency omega, and you can show, and we will see this actually in the next chapter, that omega is 1 over square root of L times C. These LC circuits are very important. They're actually used to tune radios to a given frequency, and again, I will explain this in detail in the next chapter. Now, how does the oscillation work? Let's start here with the left panel. In that particular case, the capacitor is fully charged. There is no current. All the positive charges are on the left plate, and this basically corresponds to a maximum in the potential energy. So the circuit's energy is stored all in the electric field. Now the current is flowing. You have the maximum flow of the current. At that point, the capacitor is fully discharged. And now all the circuit's energy is stored in the magnetic field. Why? Because we're inducing a strong current due to this Bmax field in the inductor. In the third panel, now the capacitor's polarity has reversed. In that particular case, the right plate is fully positively charged. We have again 0 current, and again the circuit's energy is stored all in the electric field. And then in the final panel, we have the reverse process of the second panel, where now as the capacitor is fully discharged, the current is flowing at maximum speed, however in the opposite direction. And this process repeats ad infinitum because in this idealized LC circuit we actually have no friction, meaning that the oscillation is completely undamped. With this, I'd like to thank you for your attention, and I'll see you again in the next chapter.